The first method is the method of the steepest descent. As we said, the main difference between the methods is the search direction that it will apply. So for steepest descent, the direction that we look into is the direction of steepest descent, so the direction in which it goes down fastest. So not necessarily furthest, but fastest. So what you have is you arrive in a certain theta k at a certain moment. So one of your steps brings you to theta k. And then in that point you will be looking in all different directions. And you see how you are going down in those directions. Let's make a plot for two directions. Let's say sk1 and sk2. This is my theta k where I am now. And my objective function looks like this in that direction. For the second one, this is my theta k where I am currently, and this is the shape of my objective function in this direction. So I will be taking the one where I go down fast, so I look at the tangent line, and you compare the slope of the tangent line. And so the one with the biggest slope is the one where you go down fastest, and so in this case I will select the first one, I go down fastest. How far will I go down? I will go down in this direction until I reach the minimum in this direction. So until I go all the way to the bottom of this direction. From there I say this is my new set theta k plus 1. I look again in all directions and I repeat the steps until I have a convergence. Method of steepest descent is also called the gradient method. Why? Because it applies a gradient. A gradient is nothing else but a multivariate version of the derivative. And we look for the direction of the steepest descent through the Jacobian. So the Jacobian here, this is the vector of all partial first order derivatives. So it just takes my objective function, in this case it takes my j theta, and it derives it to theta 1, theta 2, theta 3, theta n, and so on. And then we evaluate in theta k. So we evaluate in the current parameter set, and then this gives me a vector of values, not of functions, but of values, because I replace every theta parameter with a value we are in at this moment. We can make an analogy to a one-dimensional case, so a vector of partial first derivatives. If you think back at the tangent line was also defined, or at least the slope of it was defined through the derivative. So the tangent line was determined through the derivative of the function. The derivative looking at the slope or determining the slope. What we now have is a Jacobian. So we have a derivative in each direction. So we can see as the Jacobian as basically as a multivariate version of a slope. And so what it does here, it gives you the best linear approximation of j theta near the point theta k. So basically it's the same thing as what we had with the tangent line in the one-dimensional case. It's the best linear approximation of j theta near theta k. The tangent line also was the best linear approximation of my function near the point I am at. Second thing, what you can see is that for the direction we have minus. Why do we have a minus? Let's also illustrate this in the one-dimensional case. So we have just in this case, let's say x and y. We have the function and we are in this point. So this is my current parameter value. And then what I want to do, I want to go down in a direction. So we said we look at the tangent line. So here my tangent line has a positive slope. Recall my Jacobian corresponding to the slope of the tangent line. So positive slope, but I want to move to the left. So basically I want to make my values of x smaller. To make my values of x smaller, I need to subtract a value. So I don't need a positive value, I need a negative value. So with my positive slope, I have to multiply by minus, so I have to change the sign to be able to move to the left side instead of to the right side. So that's why we have minus and then minus derivative evaluated in the current parameter set. Method of steepest descent, there are different versions of it, but they are all the same method. So you can be using first order partial derivatives through the Jacobian. You can use a Taylor expansion. You can use a linear approximation of the objective function. Basically, all these methods, they boil down to the same thing. They are different versions of the same algorithm. One thing to remark is that although it's a relatively older method, let's say, it's still one of the methods that's used most often. So method of steepest descent or the gradient method is a very commonly used method. And then we said what is the optimal step size. We take the step size until we reach the minimum in that direction. So we take a step until we reach the minimum in the direction sk. So basically what we do is we look at j, so we look at the objective function, where we take step in direction sk, we take the step just as big as necessary to get the derivative 0, so to find the minimum value in that objective function. So alpha will then be alpha k, or alpha k is the alpha that minimizes this. So we step, as we said here, we are in k plus 1, and then we move down until we find the minimum in that direction. Same plot, different notation, so this is a little more clear than my drawings probably. So f corresponds to my objective function, x corresponds to my parameters, and this is then alpha times sk. So I plot my objective function in function of alpha. So I am now here, this is my current parameter set theta k, and then I move down until I reach the minimum here. So I basically take a step from here up until there. I take a step which takes me to the minimum in the objective function. This allows me to get a new parameter set. So I have my old parameter set, and then I update it by adding alpha k sk. So I add my step that I took. So alpha k, how far did I go? Sk, what direction did I go in? I add this to my previous values of the parameters. So I get alpha k minus alpha, I get theta k minus alpha k times the value of the Jacobian. And then after sufficient iterations, this will be converging. So we know that the method does converge, but convergence can be very slow. So in certain cases, you can get very slow convergence because you will have a very zigzagging path. So you get basically, instead of taking big steps to reach the minimum, you will be taking a lot of small steps to go to the same minimum. And so it will take you a lot longer than you could have. And usually this is due to a bad choice of your initial parameter set. When does this happen? Typically when the objective function forms a very narrow valley, which will become clear after this. So method of steepest descent, what happens if we look at it? So theta 1, theta 2. I have two parameters here. These are again contour lines. So recall there's a third dimension on top of it which corresponds to the value of my objective function. And each of the contour lines corresponds to one certain value of the objective function. So what I am in this point, which is my theta in step k. And then I look in the direction of this theta. I look in the direction of the steepest descent. I move this direction until when? Until here, my direction of steepest descent becomes a tangent line. So I move until direction becomes a tangent line to one of the contour plots. To one of the contours. Why? Because in this case, what you know is here my value is descending. So the value of my objective function is descending here until this. But once it touches, it means that you go away from this contour. And so the second part, your value would move up again. So here your value decreases, here your value increases. So this point where it touches another contour line, This point is the minimum point in that direction. So there you look for the new steepest descent direction, you move into that, and so you will be taking a lot of steps until you get to your your optimal solution. The smaller this is, so in this case, the smaller my ellipses are, the more steps I will need to take, because as you can see, I will be taking smaller steps because I have, or my direction becomes a tangent line faster and faster because I have this very narrow value, so I very easily touch the next contour line. In detail, so here, this is specifically for a linear problem. So a linear problem where my contour lines correspond to ellipses. I arrive here, and then it touches. I look for new directions of steepest descent. What you will note is that it is a perpendicular direction in linear case. Not in the nonlinear problem, but in a linear problem it will be a perpendicular direction. So you do have this, you go there until you reach again a tangent line, or until it again becomes a tangent line. You move in the next one, which is also perpendicular, and so on. And so the smaller the valley is here, the easier you, or the quicker you touch one of the other contour lines, and the quicker you change direction. So you get a lot of small steps until you go here to the minimum value, which is here in the center. If on the other hand, my contour lines are perfect circles, then it's a one-step procedure. If I have a perfect circle, it means that once I get here, once I have I have my, so this is my theta 0, I look in the direction of steepest descent. Steepest descent will always be the direction that you get towards the center. So you have here, and you always move there. So steepest descent for perfect circles, for contour lines which are perfect circles, are one-step procedures.